I'm John Rose Adams from the University of York, and I work on the XR Stories and the XR Network Plus projects. I'm really excited about today's talk by Jane Harris, the director of UAL's Fashion, Textiles and Technologies Institute, and Mike and Sebastian from Numerion Software. Numerion and UAL have an ongoing partnership exploring real-time rendering of textiles and garments, and they're going to be sharing today the work and findings of the latest stage of that collaboration, funded by XR Network Plus, which also involved the University of Edinburgh. And they're going to introduce themselves fully to you at the start of their talk. But first, I am just going to remind you all about what XR Network Plus is. So its full title, XR Network Plus, Virtual Production in the Digital Economy, and it provides funding and support to researchers working broadly across virtual production technologies, with the overarching aim of helping to establish a 10-year research agenda for virtual production technologies. It's a project funded by the Engineering and Physical Sciences Research Council, EPSRC, and is led by University of York in collaboration with the University of Edinburgh, University of the Arts London, Cardiff University, and Ulster University. Today's seminar will have a format that follows like this. So Jane, Mike, and Sebastian are going to talk for about 30 minutes, followed by discussions and questions from the audience. You can ask a question or make an observation via the Q&A box, which you should be able to see somewhere on your screen. Please feel free to write a question as you think it, and we'll save them all up until the talk's finished, and then we'll work through the questions. And when we get to the questions, if you want to actually ask a question verbally yourself, or make a comment or observation, you can do. You can just raise your hand with the hand button, raise hand button, and we can invite you up to talk. And we do really value and encourage your engagement, dialogue, and debate. So please do make use of the opportunity. Okay, so that's enough from me. I'm going to hand you over now to Jane, Mike, and Sebastian.
Thank you, John.
Thank you, John. We'll introduce ourselves first. So I'm Jane Harris, Professor of Digital Design and Innovation at University of the Arts, London. I also am Director of the Fashion, Textiles and Technology Institute at UAL. Mike.
Yes, so I'm the CEO of Numerion Software. We're a boutique software development house that focuses on physics simulation for interactive applications. So not for the high-end materials modeling for building ships or airplanes, but for things that are used in typically the creative industries. And we've been around since 2009. And we're actually the only company in the UK developing algorithms for physics simulation, virtual simulation from the ground up. So we don't use anybody else's software. Everything we develop is from the ground up. And so our customers have a lot of control over the software, and we are in a very strong position to help them here in the UK in particular, if they have any requirements or any issues. And Sebastian, who's going to join us on the call today, is our lead tool engineer. And maybe Sebastian, you want to just say 5 seconds about yourself?
Yeah, sure. Hi, everyone. I'm Sebastian Bindel. I'm the lead tools engineer at Numerion Software, which means I'm responsible for all customer-facing software, our plugins. I'm the technical lead on all projects, like this project, for example. And yeah, I'm excited to be here today. Thank you for having me.
And just to finish on Numerion, our main customer base is in the movie industry today. But maybe later on during Q&A, we can talk about some of the other exciting opportunities, including fashion, that we've been exploring for the last few years.
And then although Mark Parsons isn't with us, Professor Mark Parsons, who's the director of EPC, which is the exascale computing facility at Edinburgh University, isn't with us, we will also describe the engagement that we've had with Mark that this project has enabled in order for us to take this work onto a whole other level. So I think we'll switch to the presentation. Mike's going to drive the presentation. So we've done the introduction. So we thought it would be really helpful to begin by providing a little bit of context, because this project has been much longer in the making than the year or the few months that we've had funding to support this particular project. I should explain that my background is in textiles. I had a textile career, a very successful textile career up into the early 90s, and began then looking at the virtual or digital representation of textiles and cloths back in that time when computer graphic imaging was a very nascent concept. Actually, having a computer was a very nascent concept. Very few people had computers at the time, and certainly very few universities had much in terms of computing equipment. So I began this journey based in Scotland at the time, although I've worked right across the UK in the textiles field, to simply explore how computing visualization was entering our realm of what we now call the creative industries through the lens of the four main universities at the time in Scotland, or Creative Glasgow School of Art and Glasgow University, Aberdeen University, Edinburgh University and Dundee University, all of which I could safely say had pretty much one or two facilities at the time across the entire institution. And each had very different ideas as to how computing and creative computing might evolve. So from that moment, I began to look at how material knowledge might inform computing creatively as we move forward. And it really was a seed that was put in my head by somebody else who also came from a textile background, who for a moment in time was director of the Glasgow School of Art, and asked me in the late 80s, had I ever heard of virtual reality, which I hadn't. But it set off a train of thought as to how it is that the material education that I'd received and the work that I was developing at the time and was recognised as physical practice, for what it's worth at the time, how that might inform computer graphic imaging as this presentation will illustrate. So I came down to London. I did a PhD, very early PhD of its time, to look at how my material skills would inform computer graphic imaging. And to long story short, one of the earliest animations that I had the opportunity to develop with very early Arts and Humanities Research Council funding, I think it was £50,000 at the time, for a year's worth of work, had to have a risk element of failure, began to really push at the boundaries of how cloth animation may be applied within the context of a virtual archive. I'm going to ask Mike to play a movie, very short clip of an 18th century dress from the Museum of London's collection, an 18th century Spitalfields silk sackback dress. And the reason why this was complex in the time was multiple. First of all, it's about 6 layers of digital cloth at a time, and it still does, it tends to behave a little bit like cling film. So it sticks to itself. So collision detection in cloth, it's incredibly complex, even present day. And the actual animation itself, although it's a few seconds long, actually took 6 months to render at the time, with the highest level of processing power we had access to, which was quite significant. So we had an enormous amount of support from the post-production industry in Soho to help support the rendering of this animation. But it really did, the short version of the story really did rather break all our backs, because it was such a complex piece to achieve, and not least incorporating the motion capture, working with a dancer, a movement artist called Ruth Gibson, who was really brilliant in terms of us developing a character for the dress. So this wasn't just animating a piece of cloth or a garment, it was really thinking about the communication of the garment and the context within which it would potentially in the viewer's mind be positioned. Lots of things to think about, which at the time really were not being thought about. And I will just mention, because I was asked about this, before we were even constructing garments like this, and I would say that even the construction of the garment, the recording and documentation of the physical garment, and then the representation of it, working with a pattern cutter, a curator, somebody who actually sets the garment up in a three-dimensional physical form in the museum, probably took about 6 months in itself to do, just to give everybody an idea as to what was involved in representing the garment. Even accessing the garment in an archive, there are particular processes that you need to go through to be able to have permissions to appropriately, you know, use or represent a garment. We also measured all the insides of the garment and a lot of technical details around the garment, just to have the information we needed to construct this form. But in addition, at the time, there really wasn't a sense of how even avatars could be presented. So, as many viewing may know, whilst cloth and garment forms are complex to represent, so are we. So the uncanny valley will be familiar to many, and representing skin and hair at the time that I was doing this work was also incredibly complex. But before this time, before we really had developed the use of 3D software as it was evolving with cloth algorithms, cloth mechanisms, some of which worked well, some of which didn't, were still required particular and specialist expertise to navigate physical knowledge, practical knowledge, practice knowledge, material knowledge, not just digital knowledge. We actually had various experiments that we developed using motion capture to literally capture the motion of cloth, and they were incredibly successful. But again, there were very specific approaches to that, and actually modeling a complex garment form was really very difficult, because at the end of the day, motion capture is designed to capture, obviously, the motion of the body, you know, the real sort of skeletal characteristics and nature of the body, and that's what it does best. But I do have some really fantastic digital representations of material that we created working with Oxford Metrics, Vicon Oxford Metrics at the time, who were very early on as a partner in the mid-90s. And I've worked with since throughout the development of this material. So just to give you an idea, this is 2003, the 18th century dress that you've just seen the animation of. And then we make a very big leap 20 years on, and I really haven't developed the work for the last 20 years technically and aesthetically, because it just simply hasn't been viable to do so. But 20 years on, fortunately, all that I've been talking about comes to life in a different and now infamous form through the live presentation that ABBA, the rock group, have created. As many of you will know, ABBA Voyage in Pudding Lane at East Bank at Stratford in East London. And here we have effectively a feature-length film, essentially, presented in a way that it looks like the performers, ABBA the band, are physically present with us, but it is in fact a pre-rendered film, an animation essentially. And this project took 5 years to produce, £140 million worth of investment, 160 motion capture cameras, 1 billion computing and rendering hours, 1,000 CGI artists, for what is essentially a 96 minutes worth of show. Not all of which is computer graphic animation. I have to say 3D computer graphic animation, and probably only about 15 to 20 minutes of the full length film as it's effectively experienced is in fact cloth animation moving. In fact, it might even be less than that. And I think that that's illustrates how complex this field is, and the level of knowledge and the range of skills that's required in order to achieve even a pre-rendered animation still. So I go back to my 18th century dress. You don't need to go back there, might be. I go back to the 18th century dress, and actually, although we really were quite unsure as to how technically this was positioned at the time in 2003. I think ABBA Voyage 20 years on has helped us equally find an important context for that achievement. And it really was an achievement, and there was a lot of in-kind contribution to achieving that achievement. And it taught us a great deal about what in fact it would require us to have access to in terms of skills and capability, hardware and rendering power, even to begin to progress this work at the level that we were working, let alone what it is that we now can see has been achieved by ABBA Voyage. So 20 years down the line, moving on from ABBA Voyage, we had the opportunity through the Creative Industries Clusters Partnership, a series of 9 creative R&D partnerships across the UK. We, University of the Arts, led on the Business of Fashion, Textiles and Technology R&D partnership. And one of the strands of that partnership, there are at least 55 projects that we delivered. One of them, we took the opportunity to revisit how we might represent garment and textiles in an animated pre-rendered form. So we developed a project called Made in Code, Reimagining the Experience of Fashion, which took us 2 years to pull together this interdisciplinary team. Next slide, please. To address a whole series of R&D challenges as we understood them at this point in time, 20 years on from the example of the 18th century dress from the Museum of London. And the R&D challenges essentially were still the same. So cloth behavior, like cling film, not fiber-based, cloth movement driven by artificial environmental parameters, gravity, wind and air. When you're working in a three-dimensional computer graphic imaging environment, you're not just dealing with the behaviors of the material that you're trying to represent itself. You're also having to represent all the other environmental factors in order for that material to genuinely respond in a believable way to what it is that we're trying to represent. The objects and collision detection, so motion capture, skeleton, body as object, cloth on cloth, again, going back to the cling film characteristics as reference. Then the addition of motion capture. And in this case, we were fortunate enough to use a very early beta version of markerless motion capture, which meant that we could bring the public into the frame. So a new audience, a new set of participants into this overarching equation, and artificial intelligence. Human behavior and perception of experience is critical to learning more about how we can really advance this field. Material skills, the established knowledge and skills that are key to advancing this area of emergent technology, and not least real-time computer processing power, something that we're only just beginning to see globally, let alone nationally, in order to achieve a level of simulation capability that we can genuinely take into a live experience. So we worked with several companies, Numerion, obviously present, Happy Finish, Move AI, which has now been bought up by another organisation, Helition, and the fashion designer Maria Grash-Vogel. We worked with UCL's University College London's Anthropology Department, and very closely with the V&A, for whom there are really good benchmarks, certain requirements in order to genuinely pull off this combination of digital endeavour to create an experience that a museum would genuinely view as beneficial to both their own experts, their curatorial teams, those working in archive, as well as participants in the museum, across the museum, in their many forms, and of course audiences, the people that come to those kinds of environments, as to what kind of new experience we might achieve. This is a very short clip to give you an idea of what we achieved from this particular project. You got the sound, Mike? Can you hear the sound, Mike?
We don't have the sound there, Jane, but
it's okay. I mean, I'm just going to talk through it a bit in the sense that, you know, this was 2 years in the making. And essentially what we managed to achieve was as close to a real-time experience as we've seen to date. So the idea being that a member of the public comes into the museum galleries without having to dress up in a motion capture suit, which is really a significant shift. So just in their clothing, you can see, and in daylight, so not in a darkened space, it was possible to live capture an individual's motion. And for that to be installed in essentially a pre-rendered garment, but then could be driven by the motion capture within 10 minutes of that capture. I mean, I think we got close to 10 minutes. We were very limited as to the rendering power because actually the electrical capability of the museum itself, had we had any more GPUs present, we were aiming for about 5 GPUs as our rendering mechanism, and we had to dial that down to about 3 GPUs because we would have literally blown the electricity mechanism across Exhibition Road. So we obviously had to tailor what we were trying to achieve according to, you know, people forget that you need the electricity to drive things like artificial intelligence and rendering at this level of capability. So that was an interesting learning curve in itself. But essentially, we got close to this kind of real-time experience in a way that enabled the audience to see themselves in a lifelike form, life-size form, and also then on their phone as a takeaway, a bit like an NFT. And we really got some fantastic data back from this experience, working with UCL's anthropology team, who interviewed everybody that went through the process. So we also got live information from audience participants as to what it is that this experience engendered and supported. I would still say that the animation work is quite cartoon-like. It's not where we're aiming to work towards, but it is the level of quality that it was possible to achieve, which enabled a level of believability. We got that feedback most certainly from those that participated in this experience. The experience was available for 3 to 4 days. We had people sign up to the experience, and we probably had about 180 captures over that time frame, which was about the maximum that we could manage. So we've got a lot of fantastic data and feedback from the process itself, which is now invaluable because it really is a first of its kind. I would say that the whole project was probably about £1 million worth of work in total in value that as our funding went, but I would say in kind at least double that again, because there was an enormous amount of in-kind endeavour in this, just to give you an idea, and it gives you a sense of the relationship between this work and then what was achieved through ABBA Voyage. The next clip, though, is going to show you, I think, a toile, if you like, what we would call a calico toile, if you were developing a fashion piece, i.e. a trial in a cheaper fabric of a pre-rendered garment, which reaches a much higher quality of what we would envisage the cloth to achieve, were we really to go optimally to an experience that would really meet a quite different level of believability. But we are very far off from achieving this in real time. This is a pre-rendered garment form that, you know, has taken, Mike would probably give you the detail better, but much longer to render than we could ever achieve in real time. But it does give you an idea of the level of detail, and that detail is important to understand in comparison to the kind of cartoon quality that was achieved for the installation in the V&A footage that we've just shown. And this hasn't yet been embellished, so it doesn't yet have, for example, the kinds of textile surfacing and characteristics that we would expect to reach a whole other level. This is just literally the equivalent of calico toile. And so it again gives you an idea of at least the quality, the essence of the fabric that we can achieve in a pre-rendered form, without yet having the additional bells and whistles of all kinds of sort of decoration, embroidery, or other kinds of characteristics, or multiple material layers, for example, or even interacting garments in themselves. So several of these working together would in addition all be prospects moving forward. So that's just to give you a little bit of context as to what it's taken to reach this point. I'm going to hand over to Mike and Sebastian to talk about what the XR Network Plus funding has enabled us to achieve, looking through or into the window of what real-time capability would require.
Thank you, Jane. So just on your question about how long does it take? So as you say, we were rendering the video clips in the VNA in probably about 10 minutes. This is rendered with a completely different type of software, much higher quality rendering, and probably is 1,000 times slower. You know, depending on the resolution, it maybe took a day to render that video. Obviously, you can scale it out over multiple machines, but on the equivalent type of machine, it was probably a day. And for some of the renders we did for tests, which were much higher resolution, were probably taking, you know, a 16K render was probably almost a week. So high quality rendering at high resolution is still a very slow process unless you use a render farm with 100 machines on it, which obviously is pretty expensive.
So we've got these, essentially we've got these two parallel tracks, haven't we, Mike? We've got one that's dealing with the rendering side of things and what it is we're trying to push the boundaries of around that capability, and the other is maintaining the advance of the quality of the digital representation of material and dress. And they are two different. Hopefully they'll converge eventually. That's our aim, essentially.
Oh, absolutely. And you know, and then we add the simulation part to that as well. So you know, the project that we did with the XR Network Plus was really to push forward what we'd learned with the VNA, and that took a number of forms. One was, okay, so what would it take to do this in more in real time, both from a simulation point of view and also from a rendering point of view. And so from a simulation point of view, we'd already spent some time working with GPUs because we pretty much figured out that we could never get any closer to real time with CPUs because they just don't have the bandwidth we require. But even desktop GPUs, after 6 months of experimentation with multiple GPUs, we began to understand that we were still fundamentally bandwidth limited. And interestingly enough, the bandwidth limitation is a fundamental problem that the supercomputing world has to overcome, because ultimately you can have as powerful a CPU as you like, but if you can't feed it the data and you can't take the data away, it's just a doorstop. And so the XR Network Plus project enabled us to engage with Edinburgh Supercomputing Centre, and we went up there for a meeting. And although you might not think creative industries and supercomputing are a natural fit, certainly when in our field, because essentially we're architecting physics algorithms, and that's what a lot of their world is about, for whether it's for weather simulation or for engineering. And they were super interested in engaging with us to help us solve our problems, but also to understand how we were solving some of the problems we were solving, which were obviously fairly unique. I mean, our carbon software is, as I said, is not only the only solution in the UK, but also it's the fastest high quality solution in the world. So we've done some really interesting parallel processing algorithms that Edinburgh was very interested in seeing if we can translate those into a supercomputing platform. How can they apply those to other problems in aerospace or weather or whatever? And while for our problem, we would never, for those of you who don't know, a supercomputer essentially takes a very advanced GPU board, which is dedicated for data centers, and connects 10,000 of them together. And the boards themselves are very expensive. They're probably in the 25 to 50,000 pound range. And the connectivity, in my mind, is the most crazy expensive part, because each one of these cables you see here is probably £1,000 transmitter to transmit the data very fast. Because as I say, it's all about data bandwidth. And so it was very timely. I was going to Edinburgh because the next generation of data center GPU from NVIDIA, the Grace Hopper, had just been released. And we were able to talk concretely about how would our problem map onto this type of data center GPU, which is probably 10 times more bandwidth than what we have on the desktop. And so that was very, very exciting. And it was also amazing to see the supercomputing center. It was like another world. You know, when you see data power coming in the thickness of your arm, you realize that it's not your, as Jane said, you know, when we were at V&A, we were limited by 13 amps, which is just a standard household plug. But here they had some really serious power. So that was very, very interesting, and we agreed with Edinburgh that we would pursue some grant funding to make all this possible, so that Numerion could commit some time to working with them on this, and they could commit some time, and Jane could commit, UAL could commit some time, and so we've been taking that forward and applying for some funding. We've not been successful yet, but we're still looking for ways that we can engage. Because this is the only way we're going to get to real time for the simulation. So if we just maybe go back here first. So getting to real time for the simulation, and maybe the bit that I didn't mention was that the #1 request coming out of the V&A event, the #1 request people said was, we love this experience, but can we have it in real time? You know, they want to do their motion capture and they want to have it on their phone a few minutes later, not 20, 30 minutes later. Or even have a motion capture in a theatrical experience and have it replaying in some clothing in real time at high quality. You know, it's possible to do something at low quality today, but it's not believable. It's not a really believable experience. So simulation is one part of that. And then the other important part that we also sort of came away from Edinburgh going, okay, but if we solve the simulation problem, we've still got to render in real time, and we've got to render at high quality. So we started exploring a few different aspects of that within the XR Plus network project, because if we couldn't render in real time, then what's the use in simulating in real time? And we actually thought that wouldn't be so difficult, but little did we know. So the first thing we did was we just wanted to understand a little bit about the sort of variables that we might have from a rendering perspective. So if I just play a couple of videos, and maybe Jane, if you want to jump in at some point and talk at all about any of this, then please feel free to do so.
Well, I think the other thing, as I said earlier, that's underestimated is that it's not even just the cost of the computing capability, it's the electricity bill that comes with it, which we're not allowed to tell anybody about, but it is eye-watering. So I think that that's a very important factor. It goes back to why at the time we had to dial down our ambition at the V&A, because we really literally would have blown their electrical system. So, you know, we don't quite have the infrastructure in the UK yet to support this level of real time as a norm. And I think there are big questions about what as a norm that should be and how it's supported. And of course, you know, there are many opportunities to develop that norm in a sustainable form. I mean, there's tremendous technical advances that can even be made around how it is that supercomputing is supported and the infrastructure that's developed for that in order to ensure that that's a carbon efficient method of computing. And that's a whole other area of technology, which we fortunately weren't having to look at the same time. But it does bring, it brings home some the range of challenges, but also the potential. And I think that the point that you made, Mike, about the level of software physics that you are advancing just to look at cloth software in the adjacent industries that Edinburgh could specifically see from this work were really fascinating conversations that we really didn't expect. So if you cover what you've achieved.
Yeah, sure. So, and I think just one final thing on that point. I mean, hopefully new facilities are getting really serious internet connections. And I don't know about East Bank, but hopefully all those new facilities there have got 10 gigabit connections, because that was another challenge at the V&A, was that we couldn't locate this offsite and dial into it because there just wasn't enough bandwidth. But obviously, ultimately, you don't really want the actual processing on site. You want the processing in a data center and accessing it through a gigabit link. Okay, so we looked at a few different aspects using a multi-layer. So the garment you saw before had only one layer, and we started to look at, okay, so what does it mean if we start to try and render 2 layers? And there were a lot more variables, I think, than we originally thought. So obviously the interaction of the color for the layers is sort of an obvious one, but this is with a transparent, with a sort of semi-transparent lace on top that we're showing here. And then one that surprised me slightly was how you stitch the 2 layers together created a very different look to the movement of the garment. And even, if I go to the next.
And just to clarify, Mike's not just meaning how you would physically stitch the 2 garments together in the real world, in the physical world, but actually how you digitally stitch them and where you need to digitally stitch 2 different layers of fabric together to enable them to function in a digital form. So nothing really replicates the physical world, but you still need to have the knowledge of the physical world in order to then think about actually the ramifications of making the putting together of a garment, a complex garment, work, as well as working out then where you stitch it together to make it work in a digital environment. Yeah. And those are 2 different things, and the 2 different things have to work together.
And I guess we didn't make the point when we talked about the V&A, we should have done, that all those garments you saw actually started off as physical garments, and we actually use the digital patterns for those garments to create our digital version, our 3D digital version of those garments. And we use the material properties of those garments. So some of the garments you saw had panels cut on the bias, for example, and they just didn't behave properly unless we replicated the same behavior in the virtual world. And Jane and Maria Grushvogel were invaluable in helping us through their knowledge of physical materials, to actually replicate in the digital world how the real materials behaved. And we couldn't have done it without that physical material knowledge. So here we experimented also a little bit with, okay, so what happens if you don't, if you turn off collision between the layers? Then you get this rather funky blending of the 2 layers. So we turn collision off. So the character's still colliding with the upper and lower layer, but the 2 layers are not colliding with each other.
Which, whilst it's not what would happen in the real world, is the sort of thing as a textile designer you would love to achieve. And this is where you get really beautiful things occurring in happenstance, but even glitches still need to work, if you see what I mean, in order for them to be believable. So a lot of my early work, we created things that wouldn't physically exist, like a material changing color over time, almost like a hologram, for example, in some of the more contemporary pieces. And so this is a really good example of that, where Mike switched off a capability such as collision detection. And then you get the effect of another material altogether, which almost is believable, even though it's physically not achievable. And I think those are the sort of parameters that you're also attempting to try and play with for other kind of creative industry type endeavors in this sort of space. There's so much scope for creating new things, and this is a good example of that.
Yeah, we also, this is not going to show correctly on the video through a shared video, but we also looked at, okay, so what happens because we were trying to get higher quality in the final render. So what happens if we render at 8K and then sample down to 4K? And all these, I should have said that all these 3 videos were not done using the fancy software, but were produced using what Sebastian is going to talk about in a minute, which was a solution we were trying to get to with Unreal, where we had more real-time rendering at higher quality. So these were all those 3 videos I've shown you. And one thing we tried to do was render at higher quality and sample down. It definitely was an improvement, but at a huge cost for taking 4 times as long to actually render it. But the conclusion from this piece of work was there's just a lot of variables here, a lot of scope for experimentation. You know, a lot of questions about resolution and questions about viewing distance. If you're in the virtual world, you know, what viewing distance are you working for? You know, we took this to a certain way, a certain distance, and then we realized that we could spend all our time doing this, but we needed to spend time doing more on the actual rendering side of it, the real-time rendering. And so I think we've all we established was there's a lot to research here, and this was the sort of thing probably that Jane's research team was better placed to take forward. Okay, so let's keep moving on because
we've got limited time. So
time is ticking away. Yep. So let me go back to. Okay, so we spent quite a bit of our budget on getting to real-time rendering, and so maybe Sebastian, since you did all that work, you want to just quickly walk us through your 3 slides.
Sure. So basically, what we have on one end here on the right side is the movie quality that everyone would be familiar with. You go to a movie, you watch a Marvel movie, a DC movie, and it's stunning visuals. And what most people don't realize is a lot of these visuals, they're obviously rendered because we don't have aliens in real life and all these garments are rendered. But some of these frames, an individual frame, a still frame, can take days on high-end machines and farms to render. That's days on really high-end machines for one frame, and we have about 24 or 30 frames per second. So now you can imagine how much time is spent to actually render a whole movie. And that's after you're done, happy with everything on your machine, press, let's go, and then you wait for days per frame. So obviously we cannot do this for this project. On the other end, what you have is real-time rendering, and we're all familiar with PlayStation games, computer games, and these days most people would have heard of Unreal Engine, which is probably the most popular game engine. And there you achieve regularly 120 frames per second for your high-end games, and a lot of it is trickery. You know, you need to obviously always have the trade-off. A lot of it is we reduce some of the transparency. We do not do as many reflections, or we have a lot of pre-calculated optimized geometry. So we know in advance what's going in, we can optimize as well as possible, and then based on that, we can render 120 frames per second. Now for this project, we're sitting somewhere in between. We want to be as fast as possible, but we also want to be as photorealistic as possible. We have pretty high polygon count, and sorry, Mike, can you go back a frame?
Yeah, sorry.
High polygon count, but we have very dynamic data. So obviously a cloth simulation, it's something we have on the fly. We have completely new positions for each vertex of our mesh, and we need to dynamically update and render this. So we went to Unreal because Unreal is basically a existing game engine. You have full access to the source code because it's open source, and Unreal these days actually is very good at providing both ends. So you can get really photorealistic quality, and you can get the game style 120 frames per second. Now we're like, well, it can do both of this. So maybe we can go in and actually, instead of having start from ground up, instead of doing something very custom, which will be beyond the budget and the scope of this project, maybe we can take a little bit from here, a little bit from there, and let's see if we can meet somewhere in the middle. And so we started looking at this. And if you want to go to the next slide, starting from Unreal, the first thing is, okay, we have our machine. Is there anything we can do hardware optimization? And we actually realized, starting from a already pretty high card, a 3090, if we move to the 4090, we can immediately get some decent acceleration. So not only do we get the expected acceleration that comes from moving to a newer generation of this hardware, as you would expect going from an old iPhone to a new iPhone is faster, but we also get other support, which is the DLSS, which is a specific part of their like AI graphics performance software package, basically, that works only with the new hardware that gives you extra speed. So that was the first step, hardware, which luckily gave us a pretty good speed improvement. But then we were still anywhere near real time. So we had to really dive into the software, which is on the next slide. And obviously, this is months of work and research, and I just try to compress it into the 4 key points of what we did to make us jump forward in this. So Unreal Engine is a large, it's just a large project. If you download it, you get hundreds and thousands of files. You need a lot of time to really read yourself into it. And not every part is optimized. And not every part is optimized for what we want to do, because we are not the typical use case or what people would use Unreal Engine for. So we looked at the pipeline that we were using, and one of the simple things you can do is look at for loops, which is basically a processing of one thing. You say from 1 to 1,000, do this 1,000 times over certain data. And sometimes you can actually process this in parallel. So we swapped out a lot of for loops to parallel for loops, but obviously you have to be very careful because sometimes the previous iteration of the loop depends, next iteration depends on the previous one. So you have to carefully swap out this. Then the next part on the top right is we wrote custom normals tangents calculation code. So when you update your mesh, the first thing you think of is obviously the positions. My garment moves, I need to put a new position on this vertex. But in order to render it correctly, for it the shading to be right, you have to addition to the positions also update the normals and the tangents. So you get the right shading on it. Unreal luckily provides integrated automated norms and tangent calculation, which can be done on the fly and is activated by default. But we noticed that for the large amounts of data that we were pushing through, we needed something more optimized. So we wrote a custom code for this, and we got quite a speed improvement as well. And the third part is asynchronous processing. So when we're doing, when we're updating the new positions, and then we're pushing it onto the GPU, and then we're doing more calculations, a lot of this can run in, let's say, overlapping. So we're spawning several processes that are independent from each other, let them do their thing, and then at a certain point, let them meet up again, say, okay, you ready with your stuff? You ready for your stuff? Okay, let's put it together and send it off. So just some clever basically divide and conquer in the software is really helpful. And then the last point is optimized bandwidth. So the preferred data format to render dynamic meshes in Unreal is to have non-shared vertices. So each triangle is basically independent, so it can be processed in a faster way. But what we're doing for this project is we're pumping so much data onto the GPU that we need to optimize it, because otherwise we just wouldn't have the bandwidth. And Mike mentioned that earlier as well. It doesn't matter how fast your machine is if you cannot get the data in and out in time. So in order to optimize the bandwidth, we started to share vertices. So we could just pump it through faster, and actually that gave quite a speed improvement. And as a quick summary, now if you go to the next slide, so just to give an idea of what we were doing, we had these 2 layers of the garment. Each layer had on the high end 1.5 million triangles. That's around 760,000 vertices. So for 2 layers, that's 1.5 million vertices. Doing each frame, we were not only calculating the new positions, we're also calculating the new normals, the new tangents, and we're pushing this all onto the GPU and then rendering. So when we started this, and I just took Unreal out of the box, let's plug this in, let's see where we go. And I was quite disheartened at first when I
think you were crying. You were crying, basically.
Yeah, pretty much. I'm like, we're getting less than 1 frame per second. So one by one, going through these optimizations, we actually ended up going to like 19 frames per second for these high quality garments. And you can see in the graph, in the table, that if you go to slightly lower res versions, we can actually start hitting 30 frames per second, which gives you a very smooth experience. And we were quite happy with the results. And we think with some more research, some more time spent optimizing this pipeline even further, some time maybe spent optimizing the geometry, and then waiting for maybe another generation of GPUs, that we could push it even further and get smoother experiences or pump more garments through. Maybe instead of having 2 layers, maybe having 3 garments, 4 garments. And so, because once you reach 30 frames, maybe you don't need to go faster. But how about we do more than just one? And then you can have interactive experiences, like in a theater where more characters interact, except for just one person doing a cartwheel. So there are lots of things we can do, and we're quite excited about the results.
Thank you. That's brilliant. John.
Amazing, thank you, you three. That was brilliant. That was a great combination of context setting, getting into the real technical challenges, and then showing us, where you broke ground in the R&D project. That was really great. So we've got time for questions and comments. We've got two from the audience, which I'll give you both, and then I've got some other thoughts if we haven't got any more questions. If anyone in the audience wants to ask a question early, you can put your hand, you can raise your hand via the button, and we'll invite you up. But from the Q&A, so a question around AI. So do you see it posing a risk to your work, this industry, or will it be beneficial to you at some point to use in your visual prototyping stages? So where do you see AI fitting in all of this?
I think we've probably both got different views.
Go ahead.
No, Mike, you go first.
So I think without doubt AI within certainly the movie industry and maybe the creative industry more broadly is a AI driven image creation, let's say, or video creation is a great way of trying to capture a director's art director's wishes. Because for any of you that ever worked with an art director, the hardest thing is to take the gobbledygook that comes out of their mouth and turn it into something that they meant. And so being able to say to them, well, why don't you just talk to this chatbot and get a visual of what you mean, rather than me spending what would have happened in the past, me spending 3 months creating a visual for you. And then when you've got the visual you want, whether that's simulation or clothing or whatever, then let's take that forward. What people find trying to use AI for actual production or for anything of high quality are two problems. One is you end up with a head coming out of the armpit. You always get glitches, which maybe on a TikTok video is fine, but in a professional environment maybe is not so good. And then the other problem that AI has a real problem with is it's not bad at replicating still drapes of garments. So if you ask it to put this dress on another body, it can probably do an okay job of that. But it can't do motion because it has no way of understanding how a fabric moves. And since the fabric moves differently, depending on how the body parts move, it can't translate, at least today, the motion of a fabric that's been trained on one body motion to a different body motion. So momentum and motion of fabric is a very challenging problem to capture, even for us in terms of it's an unsolved problem from a material science point of view, because when fabric moves, if you think about it as a weave, it's a friction. It's constrained by friction, and even for us, we don't yet have a great way of measuring that behavior. So we can do a great job of measuring how a cloth behaves in a static drape, but we don't have a good dynamic movement measurement, basically. So I think AI has its uses, but they're not. It's certainly not the golden egg that people would like to think it is.
I'm going to come in with a related response, because the potential of AI is, as we is constantly referenced, huge. But it's a child, and it's a child that needs to be fed. And as much as we have identified significant skills requirements in the digital contexts that we're talking, and that's before we even start adding haptics, soft robotics, all sorts of other sensory capabilities that we would wish to explore. You also need the material knowledge. Well, there's a decrease in materials education at every level, from childhood to schools, to further education, to higher education. And our knowledge of material, our natural knowledge of material, even the walking into a shop and touching things and understanding what it is that we're touching. Students come to us and they don't necessarily know the difference between a silk and a cotton, even by touch. So that experience is shifting. They understand it. People tend to understand it when they see it, interestingly. So in a you know, either in a theatre in terms of costume, or a museum in terms of dress that's in a cabinet, they can read what they're looking at as being either a knit or a weave, and possibly the material, for example. But without that knowledge being fed into AI, then AI's got as much likelihood of being able to provide us with the level of experience that is being sought, that we now understand through the V&A exercise in particular, that the public love. And they really loved it. I mean, I've been to the ABBA Voyage at least 3 times just to watch responses to things. And it's very interesting. There is a whole psychology of response to moving fabric, not just the body inside the fabric. I think it's really underestimated how compelling and slightly emotional, a bit like music, that fabric moving in a quite unpredictable form, particularly to sound, but even in silence, has to a viewer. So we really underestimate all of these interfaces, whether it's visible or not, sound not being visible but tangible, obviously in a different form, but cloth being a particular interface that we frequently ignore. You know, yet we're wearing it, we sit on it, we interact with it. You know, it's extraordinary how present it is in our lives, and yet we actually don't pay it much attention. And what we're trying to do requires a lot of attention. So you have to really tune into all those characteristics and understand them in a way that then you think about AI. Actually, AI would need to be informed to that level for it to be as effective across all the different disciplines and applications that we can certainly see for this particular area of computer rendering and visual representation of material. So it's very, very complex. It's a fantastically complex computer science set of problems. And if we were really training a future generation coming through, you'd want a creative-led technology approach to skills development that really brings a properly hybrid material meets digital knowledge evolution to achieve what we could potentially achieve, which is really sky's the limit. I mean, what I know we could be capable of achieving, were all of these things to come together, is a whole new generation of experience content.
Well, thank you, Jane. So a good challenging question here. I'm going to slightly rephrase it. So the question is, at the moment, how do you ensure render results are going to be worth the time they take? And I think the loaded word is worth there. So I suppose that another version of that is, for these really, you know, supercomputer backed rendering of these really complex simulations, potentially in real time, like, I guess the question is why? And underneath that, and I think we touched on it a little bit, are there a whole range of use cases that would never need that gold standard, let's say? So I guess the direct question is, why? What's the value in getting it like all the way to the top most quality that you're aiming for?
Do you want to take that, Jane, or?
Well, I think I've just touched on it, but if I haven't, the potential for how this might be applied in live, for example, performance situations or experience scenarios in museums, etc., is massive, and it actually could change the nature of how we experience things like cinema, film, gaming, for example. And the feedback that we've had from participants in even the prototype that we had at the V&A is extremely compelling. I think that we really underestimate how limited the current potential of CGI as it's applied to date is. Much of it's controlled by much bigger multi-conglomerates than we necessarily have access to, that have managed to get away with relative cartoon to date because it's cheaper to produce. You don't need the kind of skills that we're talking about to produce it, which I think actually is rather cheating all of us, the public, everyone, from the potential of what could be achieved visually using computer imaging. And I think that's the potential. You know, why not? why have less than you could have? Why not really push the boundaries of the tools? It's like being given, you know, from a pack of 50 color pencils, one color. you know, and that's, I think, the potential.
And
I think also, sorry, just to add, I think also we've got to bear in mind that yes, it's expensive compute and expensive power, but 10 years down the road, 20 years down the road, I can do it on my phone. So, you know, we must not forget how fast the world is moving technically. And I think most worrying for me is how fast the UK is being left behind. You know, all our competitors in this space are in Korea and China. And that's going to continue if we don't spend more money in the UK on this type of technology and the supercomputer and the computing around it. We're just going to be left behind. We're just going to be a nobody in this high-tech space. You know, we're very lucky to have companies like DeepMind here, but without DeepMind, where would we be in AI? You know, we will be nowhere. And I just don't think the UK government gets that. You know, it doesn't get that at all. It talks some words, but it doesn't get that, you know, these Koreans and Chinese governments are pumping billions into this space. And we're sitting there thinking about it. And it is the future, whether people like it or not, it is the future.
Yeah. And yet I think we're uniquely positioned as a country that attends to creative industries as a significant industry, and the potential of what we could produce in the UK, we haven't even touched the tip of the iceberg of. If we really genuinely had access to the tools and the capability to develop new tools at this level, it just would be extraordinary, the potential.
Yeah.
Brilliant. Okay, we've got another question in the Q&A, and it's around scanning processes. The specific question is, I'd be interested to know more about your scanning process and the development of Gaussian splatting that the person who's asked the question has been experimenting with. I think there's a pre-question there is, do you scan textiles and garments as part of your process, or is it entirely on computer?
Oh,
so
it's a mixture. It's
okay. So yes, perfect question then. So scanning processes and what you think about newer, let's say newer methods around things like Gaussian splatting.
So we use scanning of textiles to capture the surface material properties, the surfacing properties, as an input to either a substance, for those people that know what substance is, a further processing of that before it gets applied to the actual garment during rendering. So basically, when you render a garment, you use something called a shader or shaders to create the color and maybe the fuzziness, because all garments have, you know, if you hold them to the light, they all have a little bit of fuzziness to them. So you can use shaders to do that. And the raw data that you can use to create that shader through other tools comes from a flat scanning process. Just think of it like a camera photographing a flat material. And we have not explored using Gaussian splatting at all, although it's obviously a very in thing at the moment. Numerion doesn't only sort of gets involved in rendering when we have to. It's not our core competence. Our core competence is a simulation, and but as part of the going towards real time, we felt a huge vulnerability in not being able to articulate whether you could render this in real time, because somebody would ask us, well, what about rendering? And so that's why we were very interested in understanding where technology was in terms of being able to do this in real time for rendering. So I don't think any of us can really answer the question about Gaussian splatting.
But equally, just scanning, photographing, whatever, a fabric surface, because it is so multidimensional. You only have to move a fabric a millimeter for it to change and respond to light and environment differently, etc. It's actually still quite a plastic result. And that's where, if you're from a textile background, you definitely want to interfere and evolve what Mike's just described as the shader in some form, if that's the only method you're using in order to really kind of lean into that point of believability. So even though ultimately you're probably going to be looking at an object from a distance, you might think, well, I don't need to put too much work into that. But the putting the work into it, the working into how it is that the material is described, is really extraordinarily the make or break of the believability bit. And I'm not meaning simulation, I'm meaning believability, the believability of the experience. So with the new specialist XR lab that we're setting up at UAL, we've got a new member of the team who's come from industry, and that's what they do, and they really do it at an incredibly high level. I mean, you might be surprised to know that some of what you might be looking at online when you're buying your duvet covers and sheets, etc., are often digitally produced images, not photographs, and they come from, you know, really quite a specialist experience of material knowledge to express digitally. And it's certainly not just achieved by scanning, etc., but equally it's not also geometrically achieved. It's quite a complex combination of knowledge bases.
Brilliant, thank you. There's some follow-up questions around scanning, which is really interesting. So I don't know if you can read them on your screen as well, Mike and Jane. So there's a question, I guess, about so is the approach you take to scanning versus the structure of a fabric something you might alter the balance of depending on the viewing distance, or I guess the intended viewing distance, and swap the model depending on that distance, so whether it's extreme close up or far away, I guess, as opposed to just doing it once at the highest detail and then being that.
So typically that's how it's done in games, for example, and mainly for performance reasons. But there's no sense in having vast amounts of detail. It takes a vast amount of time to render if you can't see it. So this is yet another area that needs to be explored from a from a textile point of view. It's not something that it's beyond what we're worrying about at the moment, but it's a very valid point. And you know, this rendering of believability is just a bottomless well, to be honest. And you know, for anybody who wants to understand more about the complexity of rendering something, I think a very interesting analogy is to go and read the research on facial rendering, which because over the last 30 years, the movie industry has spent a vast amount of effort to figure out how to render a human so it looks like a human. And you imagine now, down to the point that one of the things they figured out was that everybody's got a bit of fuzz on them, and if you don't have a bit of fuzz on them, you look like an android. And the same thing applies to clothing. And I think, you know, there's a lot of parallels there. You know, if you the same thing applies to material. There's just a vast amount of knowledge that has to go into making a material believable. I mean, something like a velvet, for example, is just, as James says, change the angle of the light and it looks completely different.
And I think that's where, you know, you're not often seeking something mathematically literal. And that's why I tend to avoid talking about simulation, because as soon as you start talking about simulation, you tend to be looking at mathematics, and mathematics don't tend to express what it is that the public respond well to. So you've got to then really think about the value of material knowledge in that context. And that's where we've made real inroads into making imagery really engaging in a way that you know, so some of the early animations that I did, for example, just, you know, on a loop, the same animation, 30 seconds on a loop, you know, we had to, in exhibitions, public sitting there for an hour watching that loop in silence in a portrait form, fascinated by all the different things that they saw in it, and everybody saw something different in that work. And that was a real learning curve. You know, how much you take away from, you know, computer graphic imaging is notoriously noisy and packed full of special effects, etc., whether it's pre-rendered or, you know, real time in gaming. And actually, it's really interesting to think about what we humanly bring to that experience and how compelling something can be in what might appear to be quite a simple form. And cloth's one of those things, but it does require actually a lot of detail and thinking about what it is that the viewer is going to experience. And again, it comes back to that sort of knowledge from a textile or garment position as opposed to just from a digital position. And if there were more pairings of those skill combinations, I think we'd have very different kinds of aesthetic experience as a consequence.
Yeah, brilliant. Thank you. So I think there's a question. Thank you, Michael. You've just answered in the chat, but I think it's a good one to end on as well, which is obviously there's a lot of interest in process and workflow from the audience, and obviously that's your preoccupation too. So are there any kind of key bits of research coming out of your ongoing collaboration that we can point people towards? Some key parts of that.
I think a lot of it is absorbed into other things we are doing. So I think if people have got specific questions or specific interests, it's best if they just reach out to us or through you, and we can point them in whatever direction. We're very happy to share the work we did using the XR Network Plus funding for the Unreal rendering. If anybody was interested in that. We don't consider it proprietary at all to what we're doing, but we do feel it's a significant value given that out of the box it's not what you expect, basically. As Sebastian says, sort of one end of the extreme and the other, and the two don't naturally meet out of the box. So that's, if people are interested in that, be happy to share that in some way.
Yeah, that's brilliant. Yeah, we'll work out where to do that. And I would say, there's game developers up and down the world that are looking for those kinds of solutions, practical solutions to the kinds of things that you worked out. So yeah, brilliant. Okay, well, we've reached our time, and it went very quickly, and so thank you very much. So on behalf, so from me, thank you, Jane, Mike, and Sebastian, for your time and your thought and your contributions, bringing all of that information so eloquently to us. Thank you, everyone online, for joining in, and some great questions and thoughts as well. That was really great. And yeah, that's it then. So I'm just going to say goodbye, and I think
thank you,
and thank you to the XR Network
Yes.
Plus mechanism, without which we wouldn't have been able to take this thus far. So it's been a fantastic opportunity.
Been
so
great.
thank you to you and the team as well for supporting us today.
Indeed.
Okay. Well, good luck with
everything.
Okay. All right.
Thank you. Bye-bye.
Bye.